Alright, so in this video I'm gonna be explaining another important paper with the title Sparsifying the Update Step in Graph Neural Networks. So this paper in 2024. So we are sparsifying only the update step, not the aggregation step of graph neural network, because all graph neural networks are message passing neural networks. So we conduct a structured study of the effect of sparsification on the trainable part of message passing neural network, known as the update step. We design a series of models to successively sparsify the linear transform in the update step. We propose the expander GNN with a tunable sparsification rate and the activation only GNN, which has no linear transform in the update step. In agreement with growing trend in the literature, the sparsification paradigm is changed by initializing sparse neural network architectures rather than expensively sparsifying already trained architectures. So as an extreme case of expanded GNN model, as well as an alternative to SGC, we propose activation only GNNs that remove the linear transformation layer from update step and keep nonlinearity intact. We observe the activation only models to exhibit comparable, sometimes significantly superior performance to the SGC, while being equally time and memory efficient. So in recent years, the idea of utilizing expander graphs in the design of neural networks is starting to be explored in the CNN literature. Of course, expander graphs, as in the previous videos, we used it for rewiring to avoid over squashing, also to avoid over smoothing. And the sparsification and pruning of neural network is a very active research topic. So this is the aggregation, the aggregate messages. And then in any message passing neural network, we need an update. Due to isotropic nature of graphs, arbitrary node labeling, this function needs to be permutation equivalent or invariant. It also has to be differentiable so that the framework will be end-to-end trainable. The nodes in the update, the nodes update their hidden representation based on their current representations and the received messages. After L aggregation and update iterations, depending on the downstream tasks, MPNN will either output node representations directly or generate a graph representation via a differentiable readout function. Note that various choices of aggregation, update, and readout functions are proposed in the literature. To avoid shifting from the subject of this paper, we work with the simplest and most widely used function choices, such as sum, mean, and max aggregators for aggregation, the multi-layer perceptron for the update step, and summation for readout. As an example to visualize our models in section, we use the following matrix representations of GCN's model equation. So, linear layer as a graph. The fully linear, we want to discuss how linear layers in neural networks can be represented by bipartite graphs. So the fully connected linear transform layer in MLPs can be represented by bipartite graph. and also expander linear layer. Given the bipartite graph corresponding to linear transform layer, we follow the design of this paper to construct the sparsifier by sampling its subgraph of a specific expander structure. And here they define expander sparsifier with the rows of S1 and S2. S1 and S2 are two sets of nodes. With the rows of S1 and S2 reversed, meaning that we sample nodes from S1, we call a linear layer with a computational graph an expander linear layer. We refer to the density of expander linear layer as the ratio of number of sampled connections to the number of connections in the complete bipartite graphs. So this is an illustration of the main computational step in expander GNNs. Aggregation is very normal, standard, but look at the update. The red lines in the update step represent preserved connections in MLPs, sampled as expander sparsifier structure. In the aggregation step, only a subset of the exchange messages are illustrated. So when compared to pruning algorithm, which sparsify neural network layers by iteratively removing parameters, the expander sparsifier has two advantages. The expander design assures that paths exist between consecutive layers, avoiding the risk of layer collapse that is common in many pruning algorithms, where the algorithm prunes all parameters in one layer and cuts down the flow between input and output. The expander sparsifier removes parameters at initialization and keeps the sparsified structure fixed during training, which avoids expensive computational costs stemming from adapting the neural network architecture during or after training and then retraining the network, as is done in the majority of pruning algorithms. So what is the motivation of expander linear layer? The sampling scheme samples bipartite graphs with the good expansion properties, which are commonly discussed in the field of error-correcting codes under the name of lossless expanders. Expander graphs can be informally defined to be highly connected in sparse graphs. And in this reference, the connectedness of a sparse neural network architecture was linked to complexity of given function class, which can be approximated by sparse neural networks. So utilizing neural network parameters to optimize the connectedness of network maximizes the expressivity of neural network. So this is how we implement expander linear layer. A mask M is of the same dimension as the weight matrix. So M is 1 if and only there is an edge between them, and entry-wise multiplication, these entry-wise multiplication is applied to these masks and the weight matrix so that the undesired parameters in the weight matrix are removed. So you see the aggregation and update in well-known architectures like GCN, graph isomorphism, graph SAGE, also MLP. You can see it as you have some kind of mask here, which is so mask multiplied by W is this structure is common among all of these architectures. So this is interesting to look at all well-known models as you see it as a unifying framework. So in this alternative simplification, which we refer to activation-only GNN models, we remove linear transformation instead of activation functions, such that each message passing step is immediately followed by a point-file activation function. So the activation-only GNN is written here. This proposed simplification is applicable to a wide variety of GNN models, as we will demonstrate in our extensive set of experiments. Here the nonlinear activation functions have been removed and the linear transformations have been collapsed into a single linear transformation layer. So these are the data sets that people use for graph classification, like proteins, IMDb binary, enzymes, DD. And these are the details of the approach. So they compare different expanders, if they are GCN, if the base is GIN or MLP, for different data sets.